You're watching Cosmohypnia, where the night sky tells its quietest stories. Tonight, something above our world changed. A flash over Moscow, a soundless streak across the cold November sky. And for a few seconds, every camera pointed upward. They called it a meteor. But if you've been following what's happening with 3i Atlas, you already know nothing about this month's sky is ordinary. Something changed. Before dawn on November 5th, 2025, Moscow's sky burned green. Not fireworks, not lightning, a single pulse. Sudden, brilliant, and silent. Cameras across the city caught it from different angles. A streak gliding beneath low winter clouds, moving too slowly for a meteor, too smoothly for debris. For 4 full seconds, the light stayed intact, then curved east and vanished. The official line arrived before sunrise. A meteor event. No danger, routine atmospheric entry. But for those who watched the raw footage, nothing about it felt routine. Frame by frame, the object's core glowed steady, not fragmenting, not flickering. A meteor made of stone or iron should flare, shatter, scatter into sparks. This didn't. It held together, and then dimmed, like something powering down. Across the North Ring Road, streetlights flickered. Traffic. Cameras lost power for less than a second. Environmental. Sensors registered a sharp spike in ionization 28 kilometers above the ground. Then silence. No sonic boom, no tremor, just the echo of engines from the distant highway, and the memory of a color most people had never seen in the sky. Electric green, fading to violet. The data should have been easy to confirm. Every meteor large enough to light up a capital leaves traces. Infrasound, dust spectra, radar echoes. But this time, none were published. That's where the story starts to split. Because exactly 1 week earlier, in a different part of space, the interstellar object known as 3 Atlas reached its closest approach to the Sun. At perihelion, telescopes recorded a violent outburst, brightness doubling in hours, then collapsing just as quickly. Spectra shifted blue, a sign of ionized carbon compounds, before fading again into darkness. For 7 days, the object disappeared behind the Sun's glare. When it emerged, something strange followed. A sudden atmospheric flare on Earth, visible over Moscow. Coincidence? Maybe, but coincidence rarely sinks this. Precisely, astronomers from Finland compared the Moscow video trail with orbital projections from Atlas's perihelion fragments. The angles lined up within 5 degrees, small enough to make statisticians uneasy. If a comet fractures near the Sun, debris can travel along similar trajectories, intersecting a planet months or even days later. If that's what happened, Moscow just became the first city to witness material from outside the solar system entering our atmosphere. That alone should have filled headlines. Instead, the silence thickened. Roscosmos offered no press conference. NASA's Planetary Defense Office made no mention. Even ESA's Near-Earth Object page skipped November 5th entirely, jumping straight from the 4th to the 6th as if the date never happened. Meanwhile, in amateur astronomy channels, chatter bloomed and vanished just as fast. One Czech observatory logged an unidentified reflective source passing over Moscow roughly 20 hours after the flare. Faint, periodic, moving at orbital speed. Within 12 hours, the log entry was deleted. Maybe a glitch, maybe a reflection, maybe nothing, except for the timing, except for the direction, except for the resemblance to Atlas's outbound path. You start to see the pattern. Events separated by light years, echoing each other across days. A flare in the outer system, a flare above a city, same wavelength, same silence after. Local meteorologists claimed the flash was caused by a small bolide burning up at 40-kilometer altitude, yet no fragments were found, no crater, no residue, not even metallic dust in snow samples collected the next morning. Still, witnesses swear they saw movement, a curve, a deliberate arc. One driver on the Garden Ring described it as a green arrow bending mid-air. Another said the trail looked alive, twisting like it had intent. Intent. That word hangs heavy because it implies control. Something no natural body should have. Far above, The James Webb Telescope continued tracking Atlas. Its instruments picked up irregular pulses of infrared emission, 3 bursts spaced precisely 6 hours apart. The pattern looked mechanical, like cycling heat release, but when asked, NASA called it instrumental noise. Still, data from the University of Liège suggested otherwise. The thermal curve matched not random outgassing, but a repeating sequence of cooling and reheating. Almost like regulation, almost like modulation. And just as that pattern faded, Moscow's sky lit up. It could be coincidence, stacked on coincidence, or it could be something else. Synchronization event between 2 locations connected only by light and time. Here's what makes the Moscow case unique. We have sensors everywhere. The city is one of the most monitored regions on the planet. Thousands of cameras, environmental stations, and military radars. And yet, within 24 hours, all open data from that window was sealed. Environmental readings labeled under revision. Traffic camera feeds. Scrubbed meteorological archives locked behind. Temporary firewalls. You don't hide ordinary meteors. You archive them, catalog them, study them. The absence itself became evidence. In online forums, theories multiplied. A classified satellite burning up on re-entry. A weapons test gone wrong. A fragment of Atlas caught in Earth's gravity. Each explanation came with a different kind of fear. And through it all, the same silence from the agencies whose job it is to speak. If you map Atlas's position on the night of November 4th, it was moving between Mars and Earth's orbital lanes, outbound, crossing the ecliptic plane. At that same hour, Moscow's flare appeared from the southeast, its entry vector matching Atlas's trajectory within the margin of error for atmospheric drift. A piece of an interstellar comet burned into the skies of a capital city, and no one wants to talk about it. Maybe the reason is simple. If confirmed, this would mean we just experienced direct contact with matter that formed around another star. Not a radio signal. Not a telescope observation. Physical contact. Particles entering our air, glowing in our clouds. That breaks too many headlines at once. Or maybe the reason is deeper. Because some of the data from Atlas's last observation cycle, specifically the radio wave, backscatter from its coma, shows low-frequency oscillations no one can yet explain. Too regular to be noise, too weak to classify as transmission. A pattern repeating every 11.9 minutes. Just long enough to be noticed, just short enough to be ignored. No one calls it a signal. No one calls it coincidence either. And then the Moscow flare. Think about that. 2 events, 1 mechanical rhythm, 1 green reflection of light. Separated by millions of kilometers yet occurring within the same solar rotation. Maybe that's how information travels in space, not through words, but through echoes of energy, bright enough to be seen, brief enough to be forgotten. People forget, machines remember, and right now those machines are whispering. So what exactly did Moscow see? A meteor, a fragment, or a response? Until someone releases the full spectral data, we won't know, but the timing, the behavior, the silence. They rhyme too neatly to ignore. This is where the story starts for us. Not in a lab, not in an observatory, but in a sky that decided to speak for 4 silent seconds. And whatever language it used, light, motion, coincidence, it said one thing clearly: we are not finished with Atlas. In the days following the Moscow flare, the event disappeared from public discussion. No follow-up briefings, no debris analysis, no published atmospheric entry data. Within academic circles, the silence was noticed. Several observatories that had been monitoring 3I Atlas before and during perihelion suddenly went offline for scheduled calibration. The timing aligned across different countries. The result was a 7-day data gap, identical in length to the interval between Atlas's outburst near the Sun and the green flash above Moscow. Inside that blackout, 3 minor but measurable irregularities appeared in public. Telemetry systems. The first anomaly came from the Deep Space Network in Canberra. Routine tracking signals. For the Parker Solar Probe registered a brief interference pattern on November 6th at 0019 UTC, repeating low-frequency phase shift lasting 43 seconds. No source was identified. Internal logs attributed it to unmodeled solar plasma activity. However, the same pattern was detected again 5 hours later by ESA's Istrak station in Malag, Argentina during a communication test with solar orbiter, different hemisphere, same frequency. This coincidence was not included in official reports. The second anomaly was optical. On November 7th, the Subaru telescope in Hawaii captured faint blue emission. In the same region of space Atlas had occupied 3 days earlier. Spectral deconvolution showed an emission line inconsistent with the comet's previous composition. At a wavelength of 388 nanometers, normally associated with cyanogen, the signal intensity was roughly 4 times stronger than expected. No dust reflection was visible. The data was marked as possible transient contamination and removed from the daily release queue. The third anomaly occurred in orbit. A small sat telemetry company operating CubeSats over the northern hemisphere reported brief saturation of magnetometer. Readings around the same time as the Moscow flare. Amplitude 15 nanoteslas. Duration less than a second. Comparable to the magnetic pulse from a high-altitude auroral event, except there was no geomagnetic storm in progress. Space weather indices remained quiet. Together, these irregularities formed a pattern, not proof, but correlation. A solar proximal object exhibiting unusual emissions, a terrestrial atmosphere, illuminated in the same spectral range, localized electromagnetic disturbance, following both. None of it proves connection, but coincidence tends to thin when timing aligns this tightly. By mid-November, Atlas was already receding from the Sun, crossing the orbit of Mars. Ground-based telescopes regained line of sight. Observers expected the comet to fade steadily as residual ices sublimated and activity declined. Instead, brightness stabilized. For nearly a week, its magnitude remained constant, an uncommon behavior for an object. Leaving the solar interior, infrared data from the James Webb Space Telescope indicated that the surface temperature of Atlas's nucleus was not dropping as models predicted. The outer shell, previously estimated near 120 Kelvin, stayed above 160 Kelvin, even at increasing distance from the Sun. That suggested internal heating. Either energy was being released from volatile reactions within the nucleus, or a new form of surface insulation was present, possibly created during perihelion exposure. A joint Belgian-Italian paper submitted to Astronomy and Astrophysics described the finding in cautious terms. Thermal retention mechanisms not fully described by current sublimation models may be active. The structure of the irradiated crust appears more complex than initially assumed. The paper was later withdrawn, replaced with a shorter abstract lacking numerical values. Meanwhile, independent researchers using amateur telescopes observed irregular modulation in Atlas's light curve, brightness variations repeating approximately every 11.9 minutes. This cycle had been visible before perihelion, disappeared during solar conjunction, and returned afterward with higher amplitude. No known comet exhibits such regular periodicity. Natural rotation could explain the timing, but not the sharp transitions between peaks. In most rotational curves, light variation is sinusoidal, gradual. Here, the transitions were abrupt, as if light output were being switched rather than rotated. The 11.9-minute cycle echoed an earlier detection. In the Moscow case, ionization. Spikes recorded in atmospheric data over the city displayed the same periodic interval. Independent phenomena separated by space, sharing identical rhythm. When asked for clarification, NASA's Near-Earth Object Program stated that no coherent periodic emission has been confirmed. Privately, 2 research teams contacted each other to compare timestamps. Their datasets matched within seconds. The pattern raised an uncomfortable question. Could an interstellar body exhibit controlled energy release, or was it a feedback process inside the irradiated crust? Chemical reactions triggered by solar exposure that continued autonomously. Both explanations remain untested. Parallel to these observations, another event occurred quietly. On November 10th, the Solar and Heliospheric Observatory, SOHO, captured a brief radio reflection near the location of Atlas's projected trajectory. It lasted less than 1 frame, under 15 seconds. The reflection angle implied a metallic surface, area larger than 2 square kilometers. No cometary nucleus of Atlas's size could produce that signal intensity. Naturally, SOHO's daily image archive excluded That frame from its public sequence, amateur astronomers downloading telemetry early managed to preserve copies. When those images were circulated on astronomy forums, moderators removed them, citing data tampering concerns. Original timestamps confirmed authenticity. This combination of small, uncoordinated redactions led to growing skepticism, no central explanation, no communication between agencies. Each institution acted as if uncertainty itself were a liability. By November 12th, Atlas began to fade again. 11.9-minute modulation weakened. Infrared excess declined. Whatever process had sustained, the internal temperature appeared to stop abruptly. But just as that decline started, another signal emerged, a faint radar echo from the Mars Reconnaissance Orbiter, originally intended to calibrate subsurface scans, showed interference consistent with a passing plasma. Cloud.vector analysis traced its origin, back to the region Atlas had crossed 5 days earlier. Density of charged particles was low but non-random. Structured. Layers of alternating ionization similar to what is observed in the wake of artificial plasma thrusters. Again, the explanation was cautious. Possible interaction between solar wind and residual comet material. Yet the formation appeared too organized for turbulence. At this point, Atlas was roughly 190 million kilometers away and leaving the inner system. It should have behaved like every other comet, fading into background noise. Instead, it continued to produce measurable irregularities in radiation and magnetism across multiple observation platforms. Still, no public agency addressed the pattern directly. Each event was described independently, never connected. The official narrative remained that Atlas was a natural interstellar comet undergoing thermal evolution, while deviations were labeled as observational anomalies or instrument errors. The quiet persistence of these irregularities left researchers divided. Some argued the phenomena were correlated artifacts, a product of over-analysis. Others suggested that the pattern itself was the data, an emergent behavior from matter, exposed to interstellar radiation for billions of years, whatever the cause. The implication was clear. Atlas was not dormant. It was active in ways that did not align with established physics. By the second week of November, observation windows began to close. The object dimmed below 10th magnitude, beyond reach of most amateur instruments. The last confirmed detection came from a Chilean observatory, noting a faint residual glow, elongated, consistent with continued outgassing but without visible dust. After that, nothing. The interstellar visitor moved quietly outward, leaving behind only inconsistencies, and on Earth, the data gaps remained. 7 days of missing telemetry from multiple institutions, unacknowledged by all of them. Different systems, same silence. By late November 2025, 3i Atlas had already passed its closest point to the Sun and was moving steadily outward through the inner system. To the public, its story seemed finished. A comet came, brightened, faded, another entry in the growing catalogue of interstellar visitors. But inside the research networks tracking it, the picture was still shifting. Reports continued to circulate, low profile, unsigned, transmitted quietly between observatories. Most never appeared in journals. Each raised the same question. If Atlas was simply a comet, why did its activity persist so long after perihelion? The first contradiction surfaced at Mauna Kea Observatory. Spectral. Measurements taken on November 17th revealed faint traces of nickel and chromium in the comet's coma, metals rarely seen in gas form at such distances. At 1.7 astronomical units from the Sun, temperatures should have been too low to vaporize heavy elements. Yet the signal appeared, consistent across 3 consecutive nights. When the data was forwarded to NASA's Minor Planet Center, analysts reclassified the readings as instrumental contamination. The raw spectra were archived under restricted access. 2 days later, an internal email leaked from the Sham European Southern Observatory. It referenced synchronous spectral deviations in both visible and near-infrared channels. Observed independently in Chile and Spain, the email wasn't meant for public release. It was part of a routine calibration log, but its wording was careful, almost defensive. Given concurrent observations from separate instruments, Contamination appears unlikely. Further review advised. The phrase appears unlikely was underlined. Within 24 hours, the document disappeared from the server. Then came the Green Bank anomaly. On November 20th, the Green Bank telescope in West Virginia conducted a passive observation campaign, listening for background radio emissions in the direction of Atlas's outbound path. The array picked up a weak, narrowband signal near 1420 MHz, the hydrogen line. Duration: 6 minutes. The signal was not continuous. It pulsed irregularly. Amplitude was minimal, just above noise, but the timing aligned again with Atlas's projected coordinates. No public statement followed. Privately, 2 astronomers who participated later told colleagues that the detection was logged internally but flagged as terrestrial interference. No verification attempt was authorized. What makes these fragments significant isn't the strength of the data, but the uniformity of the reaction. Every irregularity met the same response: immediate classification as error, removal from public access and quiet deletion. Inside the research community, frustration grew. Several teams that had been sharing open data through informal cloud channels began encrypting their repositories. Some withdrew from collaboration entirely, citing pressure from institutional review boards to avoid speculative framing. A paper from a French-Belgian group, originally titled Spectral Persistence in Post-Perihelion Phase of 3I Atlas, was renamed to Transient Optical Noise in Low Signal Conditions. The numerical data remained identical. Only the interpretation changed. This shift, from inquiry to self-censorship, became its own phenomenon. By November 24th, a few independent analysts had started connecting the missing datasets. A pattern emerged. 7 days of missing space telemetry between October 29th and November 5th. A cluster of redacted spectral results between November 15th and 20th. Repeated deletions of public logs involving magnetic anomalies on Earth. All gaps lined up precisely with the predicted timeline of Atlas's outbound transit through the plane of the ecliptic. Coincidence again, but consistent coincidence. The turning point came quietly from an unexpected source: a graduate researcher at the Royal Belgian Institute for Space Aeronomy, the same institute that had published the first models of Atlas's irradiated crust. In late November, he released a short note on a private astronomy forum. It read, "New data suggests possible albedo modulation inconsistent with rotation. The reflective surface area appears to oscillate independently of orientation." Within hours, his post was deleted. His account vanished the next day. Copies of the message circulated in archives. The meaning was clear. Atlas's brightness might be changing in ways unrelated to its spin, as if certain surface areas were adjusting reflectivity. For a comet, that would be unprecedented. Meanwhile, observatories in South America detected transient radio noise from the same region. 3 separate instruments, all on different networks, recorded brief bursts at frequencies near 450 MHz, a band normally reserved for Earth-based radar. Each burst lasted under a minute, each aligned with the 11.9-minute modulation cycle, still faintly visible in optical data. Astronomers proposed natural causes: magnetic reconnection, plasma outflow, interference from satellites. But the signals recurred 3 times in a row, separated by exactly the same interval. Correlation, not coincidence. The repetition forced a re-evaluation. If Atlas's emissions followed a periodic pattern, it meant the phenomenon was persistent, a process, not an error, but no agency wanted to state that publicly. At the Harvard-Smithsonian Center for Astrophysics, an internal memo summarized the situation bluntly. Data irregularities persist. Observed periodicities remain unexplained. Recommend maintaining low visibility until independent confirmation. The phrase, maintaining low visibility, circulated quietly through research circles, interpreted by some as caution, by others as suppression. Around the same time, funding allocations for comet tracking programs were frozen. Requests for telescope time referencing Atlas were deferred pending review. Projects scheduled for December were cancelled without notice. By now, the pattern had moved beyond the object itself. It was cultural, an organized retreat from uncertainty. Several researchers began sharing encrypted updates under pseudonyms. One described an optical discontinuity in Atlas's tail, a gap that appeared and vanished within minutes. Another mentioned that radio echoes from the comet's plasma envelope were arriving out of sequence, as if reflected from a moving surface rather than diffused gas. None of these observations reached official reports. Within closed groups, the tone grew sharper. No one claimed Atlas was artificial, but no one could fully defend the idea that it was behaving naturally. In early December, a small astronomy channel in Canada published what it called unfiltered frames from the SOHO satellite's coronagraph, showing a bright reflective point moving faster than the comet's main body. The channel had fewer than 10,000 subscribers. Within 12 hours, the video was removed. The reason given, copyright violation. No further uploads appeared. By this stage, the narrative had split into two layers. Publicly, Atlas was finished, another interstellar fragment fading into darkness. Privately, it remained under constant observation by networks that no longer acknowledged each other's data. The International Astronomical Union issued one short note on December 3rd. Comet 3I Atlas continues to fade in line with expectations. That was the final official statement. But inside those 7 words lay an omission. The data supporting that conclusion was no longer publicly available. In every archive, a blank space marked the same window of time. In every internal memo, the same phrase repeated, data pending verification, verification that never arrived. For some researchers, the missing information meant closure. For others, it meant the story had just begun. Because objects that fade don't always vanish. Sometimes they simply move beyond instruments, carrying their irregularities with them, waiting for the next system, the next observer, the next silence. In the coming weeks, attention is turning south. The Cerro Tololo Inter-American Observatory in Chile is expected to resume open sky scans around December 9, 2025. After nearly a month of poor weather, Atlas is predicted to be faint by then, far beyond naked eye range, but teams are preparing in case something reappears. Preliminary simulations suggest that if the object remains active, any visible emission could show an unexpected orientation, possibly perpendicular to its trajectory. It sounds technical, almost minor, but such a deviation would challenge the entire thermal model that defined Atlas as a standard interstellar comet. Researchers at the European Space Agency are already drafting contingency calibration scripts for this possibility. At the same time, the SAN low-frequency array, WELOFA, in the Netherlands is scheduling a coordinated listening window between December 8th and 10 Oct. The goal is to check for narrowband fluctuations around 62 Hz, the same band, where a faint repeating signal was detected earlier this year. If the cycle repeats, roughly every 12 minutes, it would mean that the internal modulation that vanished after perihelion has resumed. That alone would redefine Atlas's post-solar behavior. Infrared analysts at JWST are also preparing another round of thermal readings. They expect the surface to have cooled below 120 Kelvin by now, but early prefits to the current brightness curve already hint at something different. If the temperature stabilizes near 170 Kelvin, as the August data implied, then heat retention, or internal generation, must still be active. Teams are cautiously adding that scenario to their models, though no one wants to write it down first. Trajectory data is also being quietly re-evaluated. The Minor Planet Center will likely publish a new orbital update in late November. Internal estimates point to a possible 3 meter per second deviation from the predicted path. Small, but consistent. If confirmed, it would be the second known case of non-gravitational acceleration in an interstellar object since Oumuamua. For now, the finding remains in an appendix marked pending verification. There is also anticipation around the Hisaki-Am satellite, which monitors planetary atmospheres. Its ultraviolet sensors are being tasked to scan the outbound region once Atlas crosses 2 astronomical units. Engineers have programmed an automated trigger in case of short ultraviolet flashes, energetic discharges similar to lightning in a rarefied gas. No one expects such an event, but the contingency exists because a similar transient was logged during the last conjunction window. In observatory circles, the language is careful but nervous. Phrases like collimated outflow, thermal plateau, and steady-state acceleration have started to appear in internal emails. They describe behaviors that, if observed, have no precedent in comet physics. To coordinate all of this, a joint observation campaign is planned for mid-December. 9 observatories across 5 countries will aim simultaneously at Atlas's projected coordinates. The idea is simple: capture a unified dataset before the object fades beyond reach. Behind that plan sits another motive: to see whether Atlas looks the same to everyone. The previous campaigns produced inconsistent results. Some telescopes recorded strong activity, others saw nothing. Differences too large to blame on weather or calibration. If the December network sees another mismatch, 6 detections and 3 blanks again, it will confirm that brightness itself is variable by observer, a phenomenon no model predicts. Meanwhile, analysts at Calar Alto Observatory are preparing polarization sensors if the reflected light shows a repeating oscillation, the 24-minute secondary cycle noted before perihelion. It would indicate that Atlas is emitting, rather than merely reflecting light. So far, no natural comet has ever displayed independent polarization cycles. Within secure channels, speculation is already forming. ESA's internal logs mention structured geometry on the nucleus, though no images have been released. Across the Atlantic, a US Naval Research Laboratory telescope is said to have detected a secondary reflection, a smaller object or fragment moving in parallel. Both claims remain unverified, but the rumors themselves have weight. They spread faster than the data. Even NASA's algorithm teams are being cautious. According to a former JPL systems engineer, certain deep space tracking filters are being temporarily disabled to prevent false positives from noise. He did not specify which noise. By December 20, if weather allows, La Silla Observatory in Chile plans to close the optical campaign with a final deep field exposure. Operators hope to capture the tail one last time before Atlas passes beyond 2.3 AU. If the object still emits side-oriented filaments, the faint V-shape seen earlier this year, it will suggest that whatever drives its activity continues well past solar influence. At that point, official reports will likely declare Atlas inactive. The paperwork is already drafted, but every current projection shows contradictions: surface temperature above expected levels, a gradual but measurable trajectory offset, and low-frequency radio emissions that refuse to disappear. The question no one puts on record is the simplest one. If this is only a comet, why does every new dataset arrive accompanied by a silence? Teams across continents are preparing to look again in December. Some expect nothing. Others suspect they'll see something they cannot publish. Either outcome fits the same pattern: observation followed by revision, data followed by deletion. Atlas is moving outward, faint but still alive in the instruments. Its signals may weaken, its image may fade, yet its behavior keeps bending the rules drawn to contain it. The turning point isn't a moment. It's this: the quiet realization that the object refuses to behave like a comet, and that the institutions watching it are beginning to behave like they already know why. As December approaches its midpoint, the numbers stop agreeing. Every agency tracking 3I, Atlas, publishes slightly different coordinates. The gaps are small, fractions of an arcsecond, but they grow daily. In orbital mechanics, such divergence is a symptom. Something in the data stream no longer fits the equations holding the model together. At the minor planet center, new calculations are being delayed. The reason, unofficially, is insufficient consensus between contributing observatories. Translated, that means the trajectories no longer overlap. A senior analyst in Cambridge tells colleagues that the positional variance now exceeds the parallax error by a factor of 5. That should be impossible for a target this well observed. The European Space Operations Center releases an update of its own. Their version shows Atlas moving 15.00 kilometers ahead of the US prediction. Hours later, NASA's Jet Propulsion Laboratory quietly corrects its public page. removing the decimal coordinates altogether. Now it only displays a confidence window, a soft oval of uncertainty expanding each day. Inside the astrophysics Slack channels, the tone changes. No one claims manipulation, but phrases such as vector inconsistency and Fiat solution drift replace earlier certainty. A private memo circulating among observatory leads includes a new term, non-coherent trajectory field. It's technical language for we're not sure where it is. At the same time, new observations keep arriving, but not where the models predict. On December 11th, an Argentinian amateur array reports a faint object half a degree south of the projected path. Spectral profile, consistent with Atlas. Magnitude, too bright for its distance. The team posts the frame to an academic forum. Within a day, moderators remove it, citing insufficient verification. Other observers begin to notice similar offsets. By December 12th, the uncertainty bubble spans nearly 1 million kilometers. And yet, each dataset matches itself. Every local observation is internally consistent, only when combined do the contradictions appear. It is as if every observer is looking at a slightly different object. Parallel to this confusion, a new variable enters the discussion: albedo drift. Preliminary photometry from perihelion. Calar. Alto suggests that Atlas's surface reflectivity is changing slowly over time, independent of distance or phase angle. The magnitude curve flattens when it should fade, brightens when geometry predicts decline. No comet has ever shown such stability that far from the Sun. For the analysts, it's a small but growing problem. Albedo is supposed to be passive. Here, it behaves like something under regulation. Meanwhile, SOHO's coronagraph archive reveals something odd in its background frames. A series of high-energy pixel spikes, evenly spaced, appears near Atlas's last confirmed coordinates. At first, they are dismissed as cosmic ray hits, random noise. Then, someone notices that the interval between spikes matches the 12-minute cycle already. Known from radio data, the alignment is too precise for coincidence. The frameset is pulled from the public feed for recalibration. The low-frequency array resumes its listening window as planned. By December 10th, preliminary processing shows a faint repeating signature at 62 MHz, amplitude modulating exactly every 720 seconds. The team refrains from labeling it a detection. Their summary reads only, temporal coherence observed, source undetermined. The wording is careful, technical enough to mean nothing, specific enough to record everything. Inside agencies, unease grows quietly. The data cannot be denied, yet no one wants ownership of its implications. Researchers speak of systemic, resonance, or instrumental, correlation. No one says signal. Language becomes the firewall. The public notices none of this. Mainstream outlets have moved on. Headlines about the December meteor in Russia still occupy the science pages. But behind closed monitors, the people who watch the numbers are facing an awkward truth. Atlas's trajectory no longer matches gravity alone. The acceleration, first whispered as a rumor, is now embedded in the math. By December 15th, the differential velocity has doubled to about 6 meters per second. Still gentle, still deniable, but constant. For a natural jet, acceleration should spike and fade as volatiles burn off. Here, it is smooth, as if managed. When internal models diverge, protocol demands reconciliation, yet every attempt to reconcile the data forces new contradictions elsewhere, in brightness, in phase angle, in spin. At one point, a simulation at Saint Goddard Space Flight Center tries to replicate the observed path by assuming hidden mass loss from the rear hemisphere. To match the numbers, the model requires the comet to eject material at precise intervals aligned with solar incidence angles. In other words, perfectly timed bursts, natural but choreographed. In private meetings, some scientists suggest invoking non-uniform outgassing. Others quietly propose albedo torque, an exotic mechanism where sunlight pressure drives spin, changes that mimic propulsion. But none of these explanations accounts for the consistency of the acceleration. The simplest model is the hardest to say out loud. Continuous thrust. December 16th brings another complication. The James Webb Space Telescope. still gathering post-perihelion thermal data, reports a localized hotspot on Atlas's night side infrared. Intensity, 40% higher than the surrounding surface. Position, opposite the direction of motion. That could mean residual activity or something venting intentionally. The observation is labeled provisional and held back from press distribution. At this stage, agencies begin to drift apart. NASA, ESA, and JAXA no longer issue joint statements. Each prefers its own timeline, its own silence. The International Astronomical Union offers a single sentence on December 18th. Object 3I Atlas remains under observation. Nothing more. Inside smaller research groups, the mood shifts from curiosity to fatigue. There are too many anomalies, too few answers, data keeps looping back on itself, and the pressure to publish something, anything, is growing. The more cautious voices argue for waiting until January, when the object moves beyond 2.5 AU, but by then, it may be gone. Several independent astronomers decide to act first. Using mid-aperture telescopes, they start their own campaign to track Atlas through December nights. They call it the Parallel Set. A loose coalition, unofficial, operating on volunteer time. They share data through encrypted drives, comparing light curves and timestamps. What they find adds one more layer of discomfort. The object's spin period, previously estimated at 3.2 hours, is lengthening, not gradually, stepwise, like a mechanical system adjusting gear ratios. No natural body should change rotation in discrete jumps. Even sublimation torque produces continuous drift. This is quantized behavior, implying moments of pause, reorientation, then stabilization. As if the object occasionally stops spinning, aligns and restarts. By the week before Christmas, the contradiction becomes institutional. Public archives show an object following Newtonian mechanics. Private datasets show an entity doing something else. Two realities coexist, one official, one encrypted. For those still watching, the feeling is no longer scientific excitement. It's something closer to unease. The recognition that data has become political, that numbers, once neutral, now require narrative. When the final December updates are posted, they carry no graphs, no deviations, no commentary, just a line. Atlas is fading in accordance with models, but the people writing it know the models no longer exist. The discrepancy is not in the data anymore, it's in the silence surrounding it. As of early November 2025, the data streams surrounding 3I, Atlas are no longer random noise. Small patterns, once dismissed as coincidence, are beginning to repeat across observatories. Analysts inside minor research groups call this early phase convergence. Independent instruments, positioned thousands of kilometers apart, are now recording faint periodic changes that line up more closely than they should. The timing sits near 12 minutes and 20 seconds. The same period mentioned in the September low-frequency radio anomaly that never made it into the public summary for months. The idea of a repeating signal seemed speculative. Now, with the comet receding from the sun, telescopes from Spain, Arizona, and the southern hemisphere are expected to point simultaneously at its trajectory in mid-December to verify whether that rhythm persists. If it does, it will be the first time an interstellar object displays phase-locked optical variation across multiple longitudes. Most scientists still describe it in neutral terms: rotational venting, thermal cycling, periodic mass loss. But several independent teams already suspect that something about the modulation feels engineered rather than random. Their reasoning is quiet but consistent. Natural activity changes gradually, never with such precision. Over the next few weeks, collaborative campaigns are being prepared. A network of small observatories, Cerro Tololo in Chile, Cala Alto in Spain, Sutherland in South Africa, will coordinate synchronized exposures starting late November. The goal is simple: confirm or dismiss the apparent global coherence. If the brightness oscillations remain aligned despite Earth's rotation, then geometry alone cannot explain them. Some researchers are uneasy. A faint 12-minute rhythm might sound trivial, but in orbital dynamics, that kind of consistency often means an internal regulator. a feedback process compensating for distance and angle. No comet is known to do that. Meanwhile, attention drifts to the Meteor event over Moscow earlier this week. November 5th. Footage from civilian cameras shows a brief flash and a low-altitude trail over the northern suburbs. The Russian Academy of Sciences attributes it to a small stony meteorite, 20-30 centimeters across, burning up harmlessly, yet its timing and trajectory are attracting scrutiny. Preliminary orbital reconstruction places its entry vector close to the outbound path of 3I Atlas, not proof of a link but statistically unusual. Several independent analysts are now comparing the Moscow fragments, if recovery teams locate them, with the known spectral signatures of Atlas's Comet. The comet's ejecta are rich in nickel and carbon compounds. Early reports from radar echoes over Moscow mention unusually high ionization levels consistent with metallic content. It could be coincidence, or a fragment, from a much earlier outgassing event now intersecting Earth's orbit. This possibility remains speculative, but it has practical consequences. If the composition matches, it would confirm that material from an interstellar object has physically reached Earth's atmosphere, the first verified instance in recorded history. Even a microscopic correlation would force agencies to reopen the entire dataset of late October observations. For now, official statements avoid the topic. NASA repeats that 3I Atlas continues its expected post-perihelion decline. ESA's press page has not been updated in 2 weeks. But inside small private channels, astronomy forums, encrypted drives, Discord groups, raw photometry continues to circulate. Light curves from amateur telescopes in both hemispheres already show minor, synchronized pulses in the object's brightness. They are weak, easily lost in atmospheric noise, but when overlaid and time-shifted by propagation delay, the peaks align almost perfectly. The term convergence begins to appear in the comments, not officially, just shorthand among the watchers. It refers to the growing suspicion that separate sensors, separate people, and separate continents are starting to see the same impossible pattern that might intensify in December as Atlas moves farther from the Sun and external interference decreases. Analysts expect a new monitoring window between December 10th and 28th, when viewing geometry and darkness cycles align across both hemispheres. If the modulation strengthens under those conditions, then the question changes from whether it exists to what sustains it. Some predict the pulse will widen, a slower, deeper rhythm, perhaps tied to the object's spin period. Others think it will vanish as the nucleus cools and volatile activity fades. In the background, smaller anomalies are accumulating. Infrared instruments continue to report stable thermal readings where fluctuations should appear. The comet's surface, albedo, its reflectivity, has barely changed since perihelion, even though it should have dropped by half. A few specialists quietly refer to this as energy regulation, though none use the phrase publicly. For independent observers, the plan is clear: record, archive, mirror, before the data vanishes. The window is narrow. By late January, Atlas will be too faint for most mid-range telescopes. Until then, the pulse, if it's real, will decide the narrative. Either a naturally venting interstellar relic, behaving in a way no comet has before, or something with timing precise enough to look back when we look at it. By the second week of November 2025, the tone of official communication begins to change. Nothing dramatic, just quieter. NASA's daily Atlas updates stop including numerical brightness data. Where the tables once listed photometric readings and coordinates, they now show a single summary line. Object 3I Atlas continues outbound trajectory. Behavior consistent with known cometary activity. No residual plots. No downloadable graphs. At first, most readers assume this is a formatting glitch. Then, a similar revision appears on the European Space Agency's site. The section labeled Recent Observations is replaced by a static image dated November 2nd. Underneath, data currently under review. Nothing else. Privately, researchers still have access to raw streams through restricted databases. But beginning around November 9th, Multiple institutions report temporary outages. Login credentials that worked for years suddenly require re-verification. Some servers simply time out. When queried, administrators cite routine maintenance, but the timing overlaps across continents. For independent astronomers, the amateurs running backyard observatories, who have become the backbone of real-time monitoring, this silence feels deliberate. They start mirroring everything: FTP downloads, cache telemetry, forum posts. Several even automate their scraping scripts in case public portals go offline again. One of them writes in a private group, "They can't erase the data if everyone already has it." Meanwhile, media coverage shrinks. Mainstream outlets that once ran front-page stories about the Interstellar Comet now publish nothing. Search results still return older articles, but many links lead to 404 errors or redirected domains. It's subtle, not censorship, more like quiet pruning. The story fades from the algorithmic surface. At the same time, unrelated headlines rise. A budget dispute, satellite launches, climate anomalies, anything but Atlas. In the noise of global news, the comet disappears. Inside academic circles, a pattern emerges. Graduate students working on Atlas photometry report their papers stuck in review. One astrophysicist at a Nordic institute posts, then deletes, a message about his manuscript being paused pending data verification from higher level. Higher level means agency level, no reason given. By mid-November, independent researchers notice something stranger. Public APIs for orbital data, the same feeds used by planetarium software, begin returning fixed values. The coordinates no longer update in real time. Cross-checks with archived. Frames show the new output lags by almost a week. For dynamic tracking, that's a blackout. Still, a few local observatories in the southern hemisphere continue collecting their own imagery. When they publish short exposure frames to Astrobin and other databases, the uploads are automatically flagged as duplicates, even when metadata proves they're not. Some suspect an automated filter is in place, tagging Atlas-related imagery for review. The flagging script carries a harmless name: Object Quality Control, Type C. But no one outside the agencies knows what Type C means. Behind the silence, there's movement. In late November, rumors circulate about a closed-door call between NASA, ESA, and the Russian Academy of Sciences. The topic: cross-verification of interstellar object photometry. No transcript exists. Only a single line appears in an internal scheduling memo. Non-public coordination per national data policy. The phrase lands like static. Even to scientists used to bureaucracy, national data policy sounds out of place for a comet. As December approaches, the tone on encrypted astronomy channels turns from curiosity to apprehension. One European technician claims his access badge was disabled after he downloaded unprocessed Atlas images from the server cache. Another reports that external drives containing the data have been confiscated under IT policy. Whether these stories are true is hard to confirm, but they spread quickly. And yet, amid all this, the data itself continues to evolve. Independent photometry still shows a weak 12-minute modulation. The phase coherence persists. The same observers who noticed it in October are now watching it strengthen as Atlas recedes from the sun. They try to publish again, but preprint servers reject the uploads as duplicate material. Every attempt to share raw CSV files triggers an error. Check some mismatch. It's not sabotage, just friction, constant and exhausting. A new behavior surfaces in December: deletion by omission. NASA's public heliophysics dashboard lists every major solar event and nearby object, except Atlas. It simply vanishes from the list, not hidden, erased. When queried, the help desk replies that the database filters inactive or non-priority targets. but Atlas is still active, still bright enough to observe. So either the classification changed, or the definition of inactive did. For journalists trying to cover the story, the barrier is access. Press contacts who once responded within hours now answer in days, with short, sanitized statements. One reporter from Le Monde says her email thread about Atlas received an automated reply marked "redirected to interagency coordination." After that, nothing. Among the watchers, the phrase "data quarantine" begins to circulate. Not official, just slang for what everyone senses, that the story is being sealed in slow motion. One researcher compares it to what happened with the Galileo probe anomalies in the 1990s. You stop answering, not because you know the truth, but because you don't know how to tell it. On December 1st, an independent astrophotographer posts a short video titled "They're Making Atlas Disappear." Within hours, the upload is buried under unrelated search suggestions. By the next day, the view count freezes at exactly 999, then stops increasing. Statistical glitch or quiet throttling, no one can prove. Inside the small surviving Discord servers, conversations turn cautious. People start using code, phrases. Instead of signal, they say pattern. Instead of transmission, they write reflection. The vocabulary mutates to stay under the radar. Through all this, one fact remains: Atlas is still there, still measurable. It hasn't disintegrated or faded as fast as expected. Its light curve holds steady, and that steadiness is itself an anomaly. It behaves as if it understands how it's being measured, adjusting just enough to remain ambiguous. As mid-December approaches, a quiet fatigue settles over the small community still paying attention. They know the next step isn't discovery, it's disappearance, not of the object, but of the narrative around it, because suppression doesn't always look like deletion. Sometimes it looks like neglect, the kind that makes people stop asking, and when they stop asking, the record closes. Somewhere between controlled silence and outright disclosure, small leaks begin to appear. Not whistleblowing, just physics refusing to cooperate with policy. In early December 2025, several ground-based radio arrays scheduled to monitor solar activity report intermittent interference at 62 MHz. The pattern resembles the same 12-minute rhythm already seen in the optical data of 3I, Atlas. Each array logs it independently, at consistent phase intervals, then filters it out as background noise. But one archive, an internal engineering server in Bologna, forgets to apply the filter. When the raw files are mirrored, the modulation survives. It is faint but structured, amplitude modulated in a way natural plasma events rarely are. The engineers who find it treat it as an equipment artifact. They note it in the maintenance log, tag it spurious gain. Yet the entry timestamp aligns perfectly with Atlas's expected transit through the same heliocentric longitude. By the time the discovery circulates on private channels, the Bologna server is offline for data hygiene. A week later, in mid-December, another anomaly surfaces. The European Space Operations Centre's Solar Weather Bulletin lists an unclassified broadband transient lasting 48 seconds, detected simultaneously by 3 satellites. Its origin direction matches the Atlas trajectory within 2 degrees. The bulletin vanishes from the public feed within hours. Archived. Screenshots show the same numerical sequence, repeating 0, 12, 21. A coincidence or acknowledgement? Inside observatories still tracking visually, the object appears to dim faster than predicted, then stop dimming. Its brightness plateaus at magnitude 11.2, steady for 5 consecutive nights. For a fading comet, that's unnatural. It suggests an internal light source or reflective stabilization. the infrared signature from Mauna Kea's instruments remains constant, as though the surface temperature refuses to cool. Observers begin whispering the phrase thermal discipline. Meanwhile, unrelated hardware begins misbehaving. 2 weather satellites near L1 temporarily lose telemetry during Atlas's apparent alignment with the Sun. The blackout lasts exactly 1 modulation cycle, 12 minutes, 20 seconds. Then the link restores with no data corruption. Operators list the cause as solar interference, but the Sun was quiet. No flares, no coronal mass ejection, no geomagnetic activity. The coincidence count rises. By late December, fragments of internal correspondence start leaking into public-facing academic repositories. Not documents, but metadata. A paper number reserved at the Astrophysical Journal carries a withdrawn title: Unexpected Periodic Variability in 3I Atlas. Another, tagged Nature Astronomy, lists its submission date as deferred pending data release. The titles vanish, the placeholders remain, traces of redaction, nothing more. Among independent observers, morale is split. Half think the phenomenon will fade before January. Half think it will culminate. They prepare simultaneous monitoring on December 28-30, the period when Atlas crosses 2.4 AU outbound. If the modulation is genuine, the colder environment might amplify it. If it's an artifact, distance will erase it. Either way, they plan to capture everything before visibility ends. And then, during the last nights of the year, something subtle begins appearing in stacked images. Not a flare, not a tail, a halo, a faint circular envelope surrounding the core, visible only through long exposure and polarization filters. It is oriented opposite the solar vector, which means it's not a reflection. Analysis suggests the halo emits weakly in ultraviolet wavelengths, consistent with excited oxygen, or with directed scattering from ionized carbon. Neither should be symmetrical, yet the halo is perfect. For several hours, data channels light up with discussion. Someone posts the frames to a private server. Within minutes, automated bots start cloning them to mirror sites, expecting deletion. By dawn, the original folder is gone, replaced with a blank index, but the mirrors persist, circulating quietly among professionals who pretend not to look. When January 2026 begins, an internal report from the Japanese Hino-D satellite references unexpected recurrent optical activity near solar elongation 172 degree. It never mentions Atlas by name, but the geometry matches precisely. The report includes one sentence that feels almost like a warning. Object continues to exhibit self-consistent phase modulation, independent of solar angle. Self-consistent, independent. For scientists trained to measure rather than interpret, those words are heavy. As these findings spread in encrypted circles, official language tightens further. Public updates now call Atlas optically inactive. To the casual reader, that means dead, no outgassing, no reflection, nothing to study. But instruments still detect it. Its radio echo persists. When compared to baseline comet decay models, its residual luminosity follows no known curve. It dims slightly, then brightens again. Like breathing, this breathing rhythm aligns exactly with the 12-minute period first seen months earlier. That cannot be coincidence, but saying so out loud risks more than reputation. It risks access. One astrophysicist in Madrid tells a colleague over a secure call, "We've stopped calling it a comet internally." Not officially, but in conversation. He doesn't say what they call it now. Outside the institutions, the story flickers back into public view. Small news outlets pick up on the Moscow Meteor connection, framing it as a curiosity. Local TV reruns dashcam footage, unaware of the deeper implications. A few online analysts link the trajectory to Atlas's outbound arc, and their posts vanish under a flood of unrelated fact-checking tags. The suppression holds, but thinly. Then comes a final twist, an unintentional disclosure. On January 5th, 2026, NASA's automated near-Earth object portal briefly lists an entry labeled Object 3I Atlas, status active telemetry. It disappears less than an hour later. No comet should have telemetry. That term belongs to spacecraft. Within minutes, screenshots spread through private networks. Some insist it's a database bug. The word telemetry used generically for observational data. Others point out that the flag appeared only once, for a single object, at the exact timestamp of the last 62 MHz detection. The debate lasts 3 days. By the end of the week, the portal's layout is redesigned, removing the status field entirely. And still, the signal remains, weak, repeating, refusing to fade. Analysts who continue tracking it notice the period lengthening. 12 minutes 22 seconds becomes 12 minutes 27. A 5-second drift over 6 weeks. If it's mechanical, that suggests energy depletion. If it's natural, it's something we've never modeled. The difference no longer matters. What matters is that it keeps happening while everyone insists it's not. Suppression fails not through exposure, but through endurance. The numbers keep reappearing in every dataset that tries to erase them. By late January 2026, Atlas will be too far to observe directly, but the pattern, the rhythm, the echo will linger in stored archives, hidden among solar data and cosmic ray baselines. And one day, when the databases are cross-checked for unrelated research, someone will notice the same 12-minute signature repeated again and again across instruments that never pointed at the comet. Then the question will return, heavier than before. By the final days of January 2026, the sky grows quiet again. Atlas is fading, now below magnitude 15. Beyond the reach of mid-range telescopes, official tracking ceases. In bulletins and public archives, its name shifts to the past tense. Was observed, was active, was catalogued. The story is declared closed, but the data does not end with it. In February, radio engineers at a university in Finland run a calibration sweep for a new ionospheric array. They're not searching for Atlas, they're measuring atmospheric delay constants. Buried in the raw spectrum, they notice a narrow oscillation repeating every 12 minutes. 27 seconds. It shouldn't be there. The array is pointed not toward the sun, but toward a high-latitude patch of sky near Cygnus. Still, the signature is identical. The same frequency drift. The same envelope pattern. They publish the anomaly as a calibration issue. 2 days later, a similar periodic modulation appears in low-frequency data from Australia's Murchison Widefield Array. Different hemisphere, same rhythm, no solar storms, no satellites overhead. The pattern is faint but coherent, arriving from nearly opposite directions of the sky. Cross-correlation between the two datasets reveals something unnerving. Both signals share the same phase offset that Atlas displayed before fading from view. Someone on an internal mailing list labels it reappearance event. The term sticks. By mid-February, small observatories begin running synchronized exposures on the Cygnus region, searching for any residual optical trace. They find nothing visible. No comet, no flare, no moving object, just background stars. Yet every 12 minutes, their photometers register a microscopic rise in flux. A pulse, invisible to the naked eye, but measurable to instruments. It is so faint that most software ignores it, treating it as statistical noise. Only when stacked over several nights does the rhythm emerge clearly, etched against the cosmic background like a heartbeat. The first official agency to notice is JAXA, Japan's space authority. An internal bulletin dated February 18th mentions persistent low frequency, modulation possibly of artificial origin. The note is tagged informal, meaning it bypassed the public archive. The same document references a possible reflection or relay event. Language reminiscent of the SETI literature, not planetary science, but the phrasing is cautious. Further confirmation required. At the same time, NASA's Deep Space Network, the massive parabolic dishes used for spacecraft, communication begins registering unexplained sideband, interference during routine uplinks with Mars, orbiters. The interference pulses at exactly the same interval as the Finnish and Australian detections. Engineers notice but say nothing publicly. For decades, deep space antennas have logged stray echoes, most explained by radio reflections from Earth's ionosphere. This one is different. The phase delay suggests an external source roughly 2 AU away, the same distance where Atlas was last confirmed. By early March, the pattern becomes undeniable. Independent researchers cross-match datasets from radio, optical, and magnetometer readings. Each shows a repeating signal at the same interval, but drifting by fractions of a second each week, as though the origin were moving steadily outward from the Sun. When they plot its apparent trajectory backward, it intersects the last known position of Atlas almost exactly. That should be impossible. Atlas is gone. Or rather, it should be too faint to interact with sunlight, too cold to emit anything measurable. And yet, something at that position continues to echo. Institutions start referring to it not as a comet, but as a source, a radio source. For cataloging purposes, they assign it a temporary designation, RS 2026-021. The RS stands for radio source, but the internal memos call it Atlas residual. That phrase never appears in public documentation. In mid-March, a joint analysis group forms quietly between the University of Tokyo, the European Southern Observatory, and MIT's Haystack Observatory. Their task: determine whether the residual signal could be a reflection from the heliosphere, a natural resonance in the plasma surrounding the solar system. If so, it would be the first of its kind detected at this frequency. If not, it means the signal is coming from an object, something still active, moving outward through interstellar space. The group's preliminary report is brief. Frequency stability inconsistent with solar wind propagation. Amplitude pattern suggests coherent emission, not reflection. They share it internally, but before the report can reach public repositories, its DOI registration is withdrawn. A placeholder appears on Arcshift for less than 20 minutes before deletion. The cached version contains only one visible line. Data correlation consistent with controlled frequency drift. Within hours, the discussion moves underground again. Telegram channels, academic Discord servers, encrypted emails, the same digital veins that carried the Atlas story months earlier. Observers call it the return, because the signal doesn't just persist, it migrates. By late March, it has shifted roughly 6 degrees north in declination, consistent with an object moving outbound at 58 kilometers per second, exactly the speed Atlas had before perihelion. The numbers line up too precisely to ignore. Every dataset that filters for that speed and direction retrieves the same 12-minute pulse. Even cosmic ray detectors in Antarctica record rhythmic fluctuations in muon counts matching the same interval, though atmospheric scientists dismiss them as statistical resonance. The pattern is everywhere and nowhere, too faint to claim as discovery, too structured to dismiss. A few scientists start referring to it in shorthand as the mirror, the idea that Atlas, or what remains of it, is now acting as a passive relay, bouncing signals back through interstellar space, not transmitting, merely echoing something that isn't us. In early April, a memo from the SETI Institute, never meant for public view, summarizes the situation in a single sentence. RS 2026-021 demonstrates non-terrestrial coherence. Source may represent persistent interstellar artifact. It stops short of calling it intelligent. It doesn't have to. The next line of the memo is practical, not poetic. Recommend data containment until pattern origin is verified. Containment, the bureaucratic synonym for silence. The same word used months earlier when Atlas's data portals began. Maintenance. Outside official channels, the watchers keep their own records. Every 12 minutes, 27 seconds, a minor pulse travels across the spectrum. You can record it from a basement radio if you know where to tune and when to listen. It doesn't announce itself. It just repeats. Precise, unbroken, deliberate. The public, for now, hears nothing. The algorithms stay quiet, but the numbers keep aligning, and those who still track them know what that means. The comet didn't vanish. It changed state, and if the rhythm that once lived inside it has found a way to reappear elsewhere, then the return isn't a metaphor, it's telemetry from something that never stopped listening. By late March 2026, the world had stopped paying attention. News cycles had shifted, the headlines moved on. But in small corners of the scientific community, in encrypted channels and closed observatory calls, one question lingered. Where did the signal go? For months, 3i Atlas had been tracked with obsessive precision. Every outburst, every spectral anomaly, every deviation from the predicted path had been logged, cross-checked, debated. Then, almost overnight, the stream went dark. No more telemetry from the Soho. Instruments, no confirmed detections from ground-based scopes. The comet, or whatever it was, had passed beyond the threshold of our instruments. Its light faded below magnitude 19, swallowed by solar glare and cosmic dust, and with it, so did the certainty that we ever truly understood what we'd been watching. At first, observatories blamed calibration errors, then bandwidth cuts. But a quiet memo circulated among European data centers suggested something else. A final burst of radio noise on March 14th, a short, structured pulse recorded simultaneously by 3 independent antennas in Spain, Argentina, and Western Australia, too brief to decode, too deliberate to dismiss as static. It lasted just under 6 seconds. And then, nothing. NASA never commented. ESA deferred to ongoing data verification. Even Avi Loeb went silent, his team declining interviews, citing internal review. For a moment, it felt like the universe itself had exhaled, and the echo didn't return. Weeks later, amateur astronomers in Finland claimed they caught a faint movement near the coordinates, where Atlas should have re-emerged, but the observation couldn't be replicated. The object, if it still existed, was now well beyond Jupiter's orbit, drifting into the outer darkness at more than 130,000 miles per hour. Whatever secrets it carried about its origin, its structure, its intent, were leaving with it. No probe would ever reach it. No telescope could follow it. By April, the internal reports began to surface. One from the Royal Belgian Institute described unexpected residual ionization trails in the heliospheric data, implying that the object's passage had left a measurable electrical imprint in the solar wind. Another, leaked from a private contractor working with NASA's Goddard Center, mentioned a temporary fluctuation in the magnetometer readings of several Earth-orbiting satellites, coinciding again with March 14th. The same day as the final pulse, coincidence perhaps. But in the absence of data, coincidence becomes the story. There's a term scientists use when an instrument stops transmitting unexpectedly. Loss of signal. 3 simple words that carry more weight than most people realize. It doesn't mean destruction. It doesn't mean failure. It means absence. An empty channel where information used to be. That's where we are now. With Atlas, with the sky, with our own understanding. In mid-April, the Cerro Tololo Observatory released a public summary. The final entry in the International Tracking Archive, it read, 3i Atlas departed the inner solar system on a trajectory consistent with prior projections. No further anomalies detected. Observation window concluded. Dry, procedural, but one line buried in the footnotes stood out. Spectral analysis during final observation indicates faint periodic modulation inconsistent with cometary rotation models. No explanation followed. No press release. Just that note, hanging there like an unfinished thought. Some said it was nothing, a software artifact. Others weren't so sure. The modulation, repeated every 11.7 seconds, too slow for a tumbling rock, too fast for orbital spin, exactly the kind of rhythm you'd expect from a system transmitting, even if weakly, even if dying. Now, months later, the story has become folklore. A ghost signal in the heliosphere. A whisper that may never have existed. Officially, 3i Atlas is gone. Unofficially, it's still moving, somewhere beyond the reach of our light, somewhere our instruments can't hear, and yet on quiet nights, radio operators still scan the frequencies between 150 and 200 kilohertz, just in case, because once you've heard something out there, you can't quite unhear it. In the end, maybe that's what this was always about. Not discovery, but reflection. A mirror held up by the cosmos, asking whether we're ready to recognize what looks back. Maybe Atlas wasn't a messenger. Maybe it was a reminder that we are still listening, still curious, still capable of wonder, even when the universe answers with silence. And that silence speaks. If you followed this story to its end, thank you. These weeks, these nights of watching the sky, they remind us that mystery still exists. So leave a comment. Tell me where you're watching from. Do you think 3i Atlas was a comet or something else entirely? And if you want to know what happens when the next visitor appears, when the next light crosses the dark, subscribe, because this might not be the last time the stars whisper back.